Imagine scientists confirm tomorrow that an intelligent civilization exists just 1,000 light years away. Champagne corks fly, headlines scream that we are not alone, but here is the part nobody tells you. 1,000 light years means that any signal we send today will not arrive until the year 3026. Their reply will not reach us until the year 4026. By then, every person alive today will have been dead for 2,000 years. The civilization that sent the message might no longer exist. The civilization that receives the reply might not either. The closest alien minds in our galaxy could be real, alive, and thinking right now, and they could still be too far away to ever matter to us, or us to them. If you want to understand why even the nearest neighbours in our galaxy might remain forever out of reach, go ahead and hit that like button and subscribe. It truly helps this channel more than you know. Now, settle in and get yourself comfortable. Let's begin. There is a word that has quietly sabotaged every serious conversation humanity has ever had about alien life. That word is closest. It slips into sentences without resistance. The closest star. The closest habitable planet. The closest civilization. Each time we use it, our brains perform a silent, automatic translation. Closest means reachable. Closest means relevant. Closest means that if something is out there, the nearest version of it should be the one we eventually meet, contact, or at least detect. This is the assumption that feels so natural, so obvious, that almost nobody bothers to question it. And it is catastrophically wrong. The reason it feels right is not stupidity. It is evolution. Human beings spent hundreds of thousands of years surviving in environments where proximity was the single most important variable in every decision. The closest water source determined whether your tribe lived or died. The closest predator determined whether you ran or fought. The closest shelter determined whether you survived the storm. Our ancestors evolved brains wired to treat nearness as the defining characteristic of relevance. Close things matter. Distant things do not. The nearest version of any resource, threat, or opportunity is always the one worth focusing on. This cognitive architecture served us flawlessly for the entire duration of human evolution. It worked on the savannah. It worked in ancient cities. It works today when you choose the nearest grocery store over one across town. The problem is that it does not work in space. Not even slightly. When astronomers talk about the nearest star system, they are referring to Alpha Centauri, a triple star system sitting approximately 4.24 light-years from our Sun. The name Proxima Centauri belongs to the closest individual star within that system, a dim red dwarf orbiting the binary pair of Alpha Centauri A and B at a wide distance, 4.24 light-years. The number sounds small. It contains only a single digit before the decimal point. Your brain processes it and files it alongside other small numbers. 4 miles to the office, 4 hours to the airport, 4 days until the weekend. But 4.24 light-years is not a small number. It is a distance so extreme that human language buckles under the weight of trying to convey it honestly. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.24. The distance to Proxima Centauri is roughly 25 trillion miles. To put that into perspective, the farthest any human-made object has ever travelled from Earth is the Voyager 1 spacecraft, launched in 1977. Voyager 1 has been flying through space for nearly 5 decades. It travels at approximately 38,000 miles per hour, which is fast enough to cross the entire United States in under 5 minutes. After almost 50 years of continuous travel at that speed, Voyager 1 has covered roughly 15 billion miles. That is impressive by any human standard. It is also less than 0.1% of the distance to Proxima Centauri. If Voyager 1 were aimed directly at our nearest stellar neighbour, which it is not, it would arrive in approximately 75,000 years. To grasp what 75,000 years means, Consider that the entirety of recorded human civilization, every empire, every language, every written word, every war, every scientific discovery, every religion, every piece of music ever composed, fits inside the last 5,000 years. Voyager's journey to the nearest star would span 15 entire cycles of recorded civilization laid end to end. The spacecraft would arrive at a star system whose planets have completed tens of thousands of additional orbits since launch day. And this is the closest star. Not the closest civilization, the closest burning ball of hydrogen that is not our own sun. And the illusion of nearness does not stay abstract. It regenerates with every new discovery. It feeds on headlines. In November 2025, a team at the University of California, Irvine announced the detection of a habitable zone super-Earth candidate, orbiting a star called GJ251, located approximately 18 light-years from Earth. The planet sits in the orbital region where liquid water could exist on a rocky surface. The paper, published in the Astronomical Journal, described it as amenable to direct imaging by future telescopes, and the press coverage was immediate and enthusiastic, 18 light-years. The number sounded tantalizingly close, close enough to photograph, close enough to study, close enough to dream about. Then, in early 2026, a study accepted for publication in Astronomy and Astrophysics confirmed an even more striking find. The nearby star GJ887, one of the brightest red dwarfs in the sky, was shown to host at least 4 planets, with one of them, GJ887d, sitting squarely in the habitable zone. GJ887 lies just 10.7 light-years from Earth. The researchers identified it as only the second known habitable zone planet in the immediate solar neighbourhood, after Proxima Centauri b, and the closest such world after Proxima at just 10.7 light-years. The headlines practically wrote themselves: a potentially habitable world right next door, and in 2025, the ESO's Near-Infrared Planet Searcher instrument confirmed the existence of Proxima Centauri d, refining our census of the nearest planetary system to include at least 2 confirmed worlds, with Proxima b sitting in the habitable zone at 4.24 light-years. Each of these discoveries landed with a surge of excitement. Each one was reported as though proximity to Earth were the most important characteristic a planet could possess, and in a narrow astronomical sense, it is. Nearby planets are easier to observe, easier to characterize, and easier to study with current instruments. Proximity is genuinely valuable for science. But proximity is not the same as accessibility, and the language used to report these discoveries consistently blurs that distinction. Right next door, in our cosmic backyard, close enough to study. These phrases borrow the emotional warmth of human-scale nearness and drape it over distances that remain functionally infinite for any purpose beyond telescopic observation. GJ887d, at 10.7 light-years, is approximately 63 trillion miles from Earth. At the speed of the fastest spacecraft humanity has ever launched, the journey would take roughly 200,000 years. The planet is close enough to study with a sufficiently powerful telescope. It is not close enough to visit, contact, or exchange information with on any timescale that a human civilization could survive. This pattern is not new. Every generation projects reachability onto the nearest promising candidate and then watches reality strip it away. In the late 19th century, Percival Lowell convinced himself and much of the public that Mars was crisscrossed with canals built by an intelligent civilization managing a dying world's water supply. Mars was close, it was visible, it had polar caps and seasonal changes. The narrative of Martian civilization was sustained for decades, before improved observations revealed the canals to be optical illusions and the Martian surface to be a cold, irradiated desert devoid of liquid water. In the early 20th century, Venus was widely imagined as a swampy tropical world hidden beneath thick clouds. Science fiction authors populated it with jungles and oceans. Then, the Mariner missions of the 1960s revealed surface temperatures above 450 degrees Celsius and an atmosphere of crushing carbon dioxide pressure. Every nearby world that looked promising was eventually shown to be hostile, sterile, or fundamentally unlike the haven our imaginations had constructed. The same cycle is beginning again with exoplanets. Each new habitable zone detection is greeted as though the planet were a destination rather than a data point. The word habitable itself carries this bias. It does not mean inhabited. It does not even mean capable of supporting life. It means only that the planet orbits at a distance where liquid water could theoretically exist on its surface. Given the right atmospheric conditions, which we cannot yet verify for any of these worlds, the zone is defined by temperature. Everything else, atmospheric composition, magnetic field strength, geological activity, radiation environment, is unknown. Habitable zone is a statement about orbital geometry, not biology. But the phrase sounds like an invitation, and our pattern-seeking minds accept it as one. This recurring cycle of projected closeness and subsequent disappointment is not a failure of science. The discoveries are real, the planets exist, the measurements are precise. What fails is the translation from scientific finding to public meaning. Nearby habitable zone planet discovered is an accurate headline. What the reader hears is place we could go to or place where someone might live, and the distance between those two interpretations is the distance between reality and the illusion of nearness that evolution has wired into every human brain. Now layer onto this a fact that changes the entire calculation. Stars are not civilizations. A star is just a furnace. It does not think, it does not build, it does not broadcast. When we talk about the nearest alien civilization, we are not talking about the nearest star. We are talking about the nearest star that happens to host a planet, that happens to sit in the right orbital zone, that happens to have developed complex chemistry, that happens to have evolved biology, that happens to have produced intelligence, that happens to have built technology, and that happens to be doing all of this right now while we are also doing it. Each of those conditions filters the number of candidates dramatically. The galaxy contains approximately 400 billion stars. The number of those stars currently hosting a detectable technological civilization is, as far as every observation in the history of science can determine, 0. Except us. This does not mean aliens do not exist. It means that whatever the true number of civilizations is, it is small enough relative to the galaxy's volume that the nearest one could be extraordinarily far away. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the Milky Way by multiplying a chain of probabilities. The rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, the fraction of life that becomes intelligent, the fraction that builds detectable technology, and critically, the average lifespan of such a civilization. The estimates produced by this equation vary wildly depending on which values you assign to each variable. Optimistic calculations suggest millions of civilizations. Pessimistic ones suggest we might be alone. But even the optimistic versions carry a devastating spatial implication that most people overlook. If 1 million civilizations currently exist in the Milky Way, which is the high end of optimistic estimates, you can calculate the average distance between them using the galaxy's volume. The Milky Way's disk is roughly 100,000 light-years across and about 2,000 light-years thick. Distributing 1 million civilizations through that volume places the average separation at approximately 200 to 300 light-years. That sounds encouraging, until you remember what a light-year actually means. 300 light-years of separation means a round-trip message takes 600 years. If we transmitted a greeting today, the reply could not arrive until roughly the year 26. 26. No one alive today would be alive to receive it. No government currently in power would still exist. The language we sent the message in might have evolved beyond recognition. And this is the optimistic scenario. the one where 1 million civilizations are out there right now. Drop the estimate to something more conservative. Say 10,000 civilizations exist in the galaxy at this moment, a number many astrobiologists consider reasonable. Now, the average distance between neighboring civilizations climbs to approximately 1,000 light-years. A round-trip message takes 2,000 years. That is nearly as long as the entire Common Era, from the age of Augustus to the present day. Drop the estimate further. If only 100 civilizations currently exist, the average separation exceeds 5,000 light-years. At that distance, a round-trip conversation takes more than 10,000 years. When the reply arrives, the species that sent the original message may have gone extinct, evolved into something unrecognizable, or abandoned the technology that sent it. This is where the word closest begins to betray us. Our brains hear closest civilization and imagine something analogous to the closest town. A place that exists, that we could theoretically visit, that shares our time frame and our context. But the closest civilization in a galaxy of this scale is not like the closest town. It is more like a message in a bottle thrown into an ocean so vast that the bottle will wash ashore on a beach where the language inscribed on the note is no longer spoken by anyone alive. The physical distance is only the surface problem. Beneath it lies something far worse. A rupture in the very idea that distance can be overcome by patience, effort, or technology. Consider what interstellar travel would actually require, even to the nearest star, not the nearest civilization. In 2016, the Breakthrough Starshot initiative proposed using powerful ground-based lasers to accelerate gram-scale probes to 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take approximately 20 years. This is the fastest credible interstellar travel concept humans have ever seriously designed. It would deliver a probe weighing less than a paperclip, with no ability to slow down upon arrival to a single nearby star. Scaling this concept up to anything capable of carrying humans, or even a meaningful scientific payload, remains far beyond current engineering, and even this radical proposal only addresses the nearest star. Reaching a star 1,000 light-years away, at 20% of light speed would take 5,000 years. The passengers, or their remote descendants, would arrive at a destination that has aged 5,000 years since the decision to launch. The civilization they hope to contact might have risen and fallen in the interim. The concept of a mission loses coherence across these timescales. It becomes something closer to a geological event than a human endeavor. There is a subtlety here that makes the problem even sharper. When people imagine the nearest civilization, they tend to picture it as a fixed point on a map. Something sitting still, waiting to be found, like a city on a globe. But civilizations are not fixed points. They are temporary events. They flicker into existence, burn for a while, and go out. The question is not just how far away the nearest civilization is in space. It is how far away it is in time. And those two distances compound each other in ways that destroy the intuitive comfort of proximity. Recent quantitative analyses of the Fermi paradox, working backward from the observed silence to estimate how long civilizations might actually survive, suggest that if intelligent life is common in the galaxy, civilizational lifetimes may be far shorter than popular imagination assumes, potentially too brief to bridge even the nearest interstellar gaps. Their analysis concluded that under optimistic assumptions about how frequently intelligent life arises, the absence of any detected extraterrestrial signal imposes an upper limit on civilizational lifetimes of approximately 5,000 years under the most favorable conditions. 5,000 years, that is roughly the span from the invention of writing to the present day. If this estimate is even approximately correct, it means that the average technological civilization does not last long enough to bridge the distances separating it from its neighbors. It blooms, it broadcasts, and it goes silent long before any reply could arrive from the nearest listener. This finding does not prove that civilizations are short-lived. It is an inference drawn from the observed silence, a constraint imposed by the data we have. But it illustrates a principle that most popular discussions of alien life ignore completely. Distance is not the only barrier. Duration matters just as much. A civilization that lasts 10,000 years in a galaxy where the nearest neighbour is 5,000 light-years away has a narrow window in which contact is even theoretically possible. And that window assumes both civilizations are broadcasting, listening, aligned in frequency, and pointed in each other's direction. Remove any one of those conditions and the window slams shut. The psychological weight of this realization is difficult to overstate. For decades, popular science has trained the public to think of the search for alien life as primarily a problem of detection technology. Build a bigger telescope. Listen on more frequencies. Scan more stars. The implicit promise is that progress is linear. Every year we search more of the sky, we get closer to finding something. And in a narrow technical sense, this is true. Programs like Breakthrough Listen now scan thousands of nearby stars across billions of radio channels, expanding the search further every year. Each year the coverage grows, but covering more ground does not help if the ground itself is the problem. You can build a telescope capable of detecting a transmitter anywhere in the galaxy. If the nearest transmitter went silent 3,000 years before you turned your telescope on, you will find nothing. The sky will be quiet, not because it was always empty, but because you arrived too late. There is a deeper layer still. The word closest implies a kind of stability. The closest grocery store will still be there tomorrow. The closest friend still lives at the same address. But in galactic terms, closest is a snapshot, not a permanent condition. Stars move, the Milky Way rotates. Stellar orbits are not fixed circles but complex paths, influenced by gravitational interactions across the entire disk. The star that is closest to us today was not closest to us 1,000,000 years ago and will not be closest to us 1,000,000 years from now. Proxima Centauri is currently our nearest stellar neighbour, but it is slowly moving relative to our Sun. In approximately 30,000 years, it will no longer hold that title. The stars themselves shuffle through the galaxy on timescales that dwarf any civilization's lifespan. The nearest civilization is not a permanent neighbour. It is a momentary alignment, like two ships passing in a fog so thick that neither one sees the other's lights. What this means in practice is that the concept of a nearest civilization may be fundamentally incoherent when applied across civilizational timescales. The civilization that was nearest to us 10,000 years ago occupied a completely different region of the galaxy than the one that might be nearest to us 10,000 years from now. If civilizations are short-lived, then the nearest one at any given moment is a moving target, defined by a coincidence of spatial proximity and temporal overlap that may never repeat. You cannot plan a mission to reach a destination that will not exist by the time you arrive. You cannot sustain a conversation with a correspondent who will not be listening by the time your words cross the void. This is the first crack in the comforting fiction of cosmic nearness. Closest is a word that evolved on a planet where the farthest journey took months and the oldest institutions lasted centuries. We borrowed that word and applied it to a cosmos where the shortest meaningful distances take millennia to cross, and the oldest known civilizations may not last long enough to matter at those scales. The word still sounds reassuring. It still triggers the ancient cognitive reflex that proximity equals accessibility. But the reassurance is hollow. In the context of interstellar distance, closest does not mean reachable. It does not mean detectable. It does not even mean relevant. It means only that among all the impossible separations in the galaxy, this one happens to be the least impossible. And the least impossible distance in a galaxy, 100,000 light-years across, can still be a distance so great that no signal, no ship, and no meaningful exchange will ever cross it within the lifespan of the civilizations on either end. But perhaps this analysis is too focused on the physical gap. After all, we do not need to travel to an alien civilization to make contact. We only need to send a signal. Light moves at the fastest speed the universe permits. Radio waves, laser pulses, any electromagnetic transmission races across the void at 300,000 kilometers per second. Surely, even if we cannot visit our nearest neighbors, we can at least talk to them. Surely the speed of light solves the distance problem, even if spacecraft cannot. It does not, and the reason it does not reveals a second, deeper layer of the problem. One that transforms the idea of cosmic communication from a technical challenge into something closer to a physical impossibility. Because the speed of light is not fast enough, not nearly fast enough, and what that speed limit does to the concept of a conversation between civilizations is something most people have never seriously considered. Light is the fastest thing in the universe. Nothing outruns it. No particle, no signal, no piece of information can travel through space faster than 300,000 kilometers per second. This is not a technological limitation that future engineering might overcome. It is a fundamental law of physics, woven into the structure of space-time itself. Einstein's special relativity, confirmed by over a century of experimental evidence, establishes the speed of light as an absolute cosmic speed limit. Nothing that carries information can exceed it, ever. This means that light is not just fast, it is the fastest that communication can ever be, regardless of how advanced a civilization becomes. If two civilizations want to exchange a single sentence across a distance of 1,000 light-years, the minimum possible time for that exchange is 2,000 years. Not because their radios are weak, not because their engineering is primitive, because the universe does not permit faster delivery. The signal travels at the maximum speed reality allows, and it still takes a millennium to arrive. 2,000 years is not a delay, it is an extinction event for meaning. Consider what the world looked like 2,000 years ago. The Roman Empire controlled the Mediterranean. The Han dynasty ruled China. The Americas were populated by civilizations that would not encounter Europeans for another 15 centuries. No language spoken today existed in its current form. No nation currently on any map had been founded. No political ideology, no scientific framework, no cultural institution that shapes modern life had yet been conceived. If the Roman Senate had transmitted a message into space in the year 26, and a civilization 1,000 light-years away received it, decoded it, and sent a reply, that reply would be arriving right about now. The Roman Senate has been dead for nearly 1,500 years. The language the message was written in is no longer spoken natively by anyone on Earth. The civilization that sent it no longer exists in any recognizable form. The reply would be an answer to a question asked by ghosts, delivered to strangers who have no memory of the original conversation. This is not a contrived thought experiment. This is the actual, physical reality of interstellar communication at even modest galactic distances. 1,000 light-years is not far by galactic standards. The Milky Way is 100,000 light-years across. 1,000 light-years represents 1% of the galaxy's diameter. If the galaxy were a football field, 1,000 light-years would be roughly 3 feet. And even across that single foot of cosmic real estate, a round-trip conversation outlasts the entire recorded history of the civilizations attempting it. The problem deepens when you examine what conversation actually requires. A conversation is not merely the transmission of data from point A to point B. It is a reciprocal exchange in which each participant responds to the other's most recent statement. It requires shared context. Both parties must understand what is being discussed, why it matters, and what a useful response would look like. On Earth, conversations work because they happen in real time or near real time. You say something, the other person hears it, processes it, and responds within seconds. Even asynchronous communication like email functions, because the delay is measured in hours or days, a time frame within which both parties retain the context of the exchange. A delay of 2,000 years annihilates context. It does not merely slow the conversation, it ensures that by the time a response arrives, neither party remembers or cares about the question. The civilizations involved have changed so completely that the exchange carries no more meaning than finding a clay tablet inscribed in a dead language buried under a city that no longer exists. You can study it. You can admire it. But you cannot continue the conversation it was part of, because that conversation ended centuries before you were born. Some optimists argue that even a one-way detection would be transformative. We would not need a conversation. Simply knowing that another civilization exists, or once existed, would change everything about how humanity understands its place in the universe. This is true. A confirmed detection of an alien signal would be the most important discovery in human history, regardless of whether we could reply or be understood. But this argument subtly concedes the central point. If the best we can hope for is a one-way detection of a signal sent by a civilization that may already be gone, then we are not describing contact. We are describing archaeology. We would be studying the remains of someone else's existence, not participating in a shared experience. The word contact implies mutuality. It implies that both parties are affected, that something flows between them. Receiving a 10,000-year-old signal from a dead civilization is not contact, it is eavesdropping on a ghost. Before confronting the physics of signal degradation, it is worth pausing on a dimension of the detection problem that is often mentioned in passing, but rarely examined in full. The energy economics of interstellar beacons. When people imagine an alien civilization announcing its presence to the galaxy, they tend to picture something like a lighthouse, a bright signal sweeping the sky, visible to anyone who happens to look. The metaphor feels intuitive, but the mathematics of broadcasting across interstellar distances make a cosmic lighthouse one of the most extravagant engineering projects imaginable. Consider what it would take to produce a radio signal detectable at 1,000 light-years. The power required depends on several factors: the frequency, the bandwidth of the signal, the sensitivity of the receiver, and critically, whether the signal is broadcast in all directions simultaneously or focused into a narrow beam aimed at a specific target. Omnidirectional broadcasting is the most generous option. It ensures that every star within range has a chance of detecting you, regardless of where they sit relative to your position. But omnidirectional transmission is fantastically wasteful. The signal energy spreads across the surface of an ever-expanding sphere. By 1,000 light-years, that sphere has a surface area so enormous that the energy falling on any particular star system is negligible. To produce a signal detectable by a receiver comparable to the Green Bank telescope at a distance of 1,000 light-years, an omnidirectional transmitter would need to radiate at power levels measured in tens of petawatts or higher, sustained continuously. For reference, the total power consumption of all human civilization is roughly 18 terawatts. An omnidirectional interstellar beacon visible across even a modest fraction of the galaxy would require energy output exceeding humanity's entire current energy budget by thousands of times or more. Maintaining such a beacon for centuries or millennia would demand energy infrastructure on a scale that approaches capturing a significant fraction of a star's total luminosity. Directed beaming reduces the energy requirement dramatically, but introduces its own costs. A tightly focused beam can concentrate power into a narrow cone aimed at a specific star, reducing the required transmitter power by factors of millions or billions compared to omnidirectional broadcasting. The Arecibo Observatory's planetary radar, one of the most powerful directed signals humanity ever produced, operated at roughly 1 million watts and could theoretically be detected at distances of hundreds or even thousands of light-years by a receiver of comparable sensitivity. But a directed beam illuminates only a tiny sliver of the sky. To cover the galaxy systematically, a civilization would need to aim its beam at each candidate star individually, transmitting for long enough that the signal is detectable, then rotating to the next target. With hundreds of billions of stars in the Milky Way, a complete survey conducted this way would take longer than most civilizations are likely to last, even if each target received only seconds of illumination. The energy problem creates a paradox that sits at the heart of the detection question. The civilizations most likely to be detected are the ones spending the most energy on broadcasting. But spending energy on broadcasting means diverting resources from other priorities: food production, infrastructure, defense, science. A civilization that allocates a significant fraction of its energy budget to a beacon aimed at strangers who may not exist is a civilization making an extraordinary bet. It is wagering that someone is listening, that they will receive the signal, that they will understand it, and that some form of return, whether information, alliance, or simply the knowledge of being heard, will justify the expenditure. For a short-lived civilization, this bet is particularly poor. The return, if it comes at all, arrives centuries or millennia after the investment is made. The generation that pays the cost will never live to see the benefit. Every interstellar beacon is an act of intergenerational altruism, so extreme that it borders on self-sacrifice. And the economic logic of such investments may explain why even civilizations capable of building beacons choose not to. The silence we observe might not reflect an empty galaxy. It might reflect a galaxy full of civilizations that ran the numbers and decided the cost was not worth paying. But even one-way detection faces crushing physical obstacles. The inverse square law governs how electromagnetic signals weaken with distance. When a radio transmitter broadcasts a signal, that signal spreads outward in an expanding sphere. The surface area of that sphere grows with the square of the distance from the source. This means the energy per unit area decreases rapidly. Double the distance, and the signal becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. At 1,000 light-years, a signal is diluted by a factor that involves squaring a number with 16 digits. The attenuation is not gradual, it is savage. To illustrate what this means practically, consider Earth's own electromagnetic output. Humanity has been broadcasting radio signals since the early 20th century. Television transmissions, military radar, commercial radio, all of these have been leaking into space for roughly a century. This expanding shell of radio noise, sometimes called our radiosphere, extends approximately 100 light-years from Earth in every direction. 100 light-years sounds like a meaningful reach. It encompasses several thousand stars, but here is the critical detail. Those signals were never designed for interstellar communication. They were designed to reach antennas on the same planet. By the time our television broadcasts have travelled even a few light-years, they have weakened to levels far below what any realistic receiver could detect. At 100 light-years, they are indistinguishable from the natural background noise of the cosmos. Our accidental electromagnetic leakage is functionally invisible beyond our immediate stellar neighbourhood. What about deliberate signals? In 2025, a research team led by Sophia Sheikh at the SETI Institute published a landmark study titled Earth Detecting Earth, which modelled the detectability of various human technosignatures from an extraterrestrial perspective. The study found that Earth's most powerful deliberate transmissions, specifically planetary radar pulses from the now decommissioned Arecibo Observatory, could theoretically be detected from distances up to approximately 12,000 light-years, but only by a receiver with sensitivity comparable to our own best instruments, pointed in exactly the right direction, tuned to exactly the right frequency, at exactly the right time. Passive emissions like broadcast television and cellular signals were detectable from far shorter ranges, most fading into noise well within a single light-year. The study concluded that detecting a civilization like ours from typical interstellar distances would require either extraordinarily powerful deliberate beacons or receiver technology far beyond what we currently possess. Even our loudest intentional shout into the cosmos is a whisper measured against the vast silence of the galaxy. This creates an asymmetry that undermines the entire logic of passive listening. When SETI researchers scan the sky for alien signals, they implicitly assume that at least some civilizations are building powerful transmitters and beaming energy toward us, either deliberately or accidentally. But the energy requirements for a signal detectable across thousands of light-years are immense. A civilization wanting to send a message readable at 1,000 light-years would need to focus enormous power into a narrow beam aimed precisely at the target star. Broadcasting in all directions simultaneously would require energy outputs rivaling the total luminosity of a star. No known technology can achieve this. Directed beaming is more feasible, but it requires knowing exactly where to aim, which requires already knowing where the target civilization is. And you cannot know where to aim if they have not announced their presence, which they cannot do without knowing where to aim their own signal. This chicken and egg problem is not a trivial technical hurdle. It is a structural feature of interstellar communication that scales with distance. The farther apart two civilizations are, the more precisely they must aim, the more energy they must spend, and the less likely they are to achieve mutual detection by chance. The Breakthrough Listen initiative, currently the most comprehensive search for extraterrestrial intelligence in human history, illustrates both the progress and the limitations of modern SETI. Operating since 2015 with funding from the Breakthrough Initiatives Foundation, the project uses some of the world's most sensitive radio telescopes, including the 100-meter Green Bank telescope in West Virginia and the 64-dish Meerkat array in South Africa, to scan nearby stars, the galactic plane, and even other galaxies for narrowband signals that could indicate artificial origin. The search covers billions of radio channels across wide frequency ranges and employs sophisticated algorithms to distinguish potential alien transmissions from the overwhelming torrent of human-generated radio interference. The results so far are instructive. Breakthrough Listen has surveyed thousands of nearby stars, examined the centers of nearby galaxies, and in 2025 conducted targeted observations of the interstellar object 3I Atlas using both the Allen Telescope Array and the Green Bank Telescope. In every case, the result has been the same. No confirmed technosignatures detected. Not a single verified alien signal among billions of candidate detections, all of which were ultimately attributed to terrestrial radio frequency interference or natural astrophysical phenomena. This does not mean aliens are not out there. It means that even with humanity's most sensitive instruments scanning the nearest and most promising targets, the galaxy remains stubbornly silent. The silence is not proof of absence, but it is consistent with a universe in which detectable civilizations are either extremely rare, extremely quiet, or separated by distances and timescales that make mutual detection fantastically unlikely. The most comprehensive illustration of this silence arrived in August 2025, when the SETI at Home project published its final data analysis. SETI at Home was, for over 2 decades, the largest distributed computing project in history. Launched in 1999, it enlisted millions of volunteers worldwide to donate idle processing power from their personal computers to analyze radio telescope data collected at the Arecibo Observatory in Puerto Rico. The dataset spanned 14 years of observations covering nearly the entire sky visible to the telescope. The raw data contained billions of candidate detections, brief excesses of narrowband power, pulsed signals, patterns that warranted closer inspection. Each candidate was processed, classified, and ranked by probability of artificial origin. The scale of the analysis is worth appreciating. Billions of individual detections were sifted. Millions of computers contributed processing cycles. The effort represented the most exhaustive search ever conducted through a single astronomical dataset for evidence of extraterrestrial technological activity. The final results, published by David Anderson, Eric Korpela, and their collaborators, identified numerous signal candidates, groups of detections that could plausibly originate from a single cosmic source. Each candidate was then subjected to rigorous filtering to remove signals attributable to known radio frequency interference, satellite transmissions, aircraft, or instrumental artifacts. The conclusion was unambiguous. No credible extraterrestrial signal was identified in the entire dataset. Every candidate that survived initial screening was ultimately explained by terrestrial or instrumental sources. 14 years of continuous observation, nearly complete sky coverage, billions of detections, 0 confirmed alien transmissions. The result did not surprise the SETI community. Researchers had long understood that the probability of detection in any single survey is low, given the vastness of the search space in frequency, time, and sky position. But the SETI at home result gave that abstract understanding a concrete weight. This was not a brief survey of a few hundred stars. It was a 14-year census of the radio sky, and it returned silence. The silence is not damning, it is informative. It tells us that within the volume of space accessible to Arecibo's sensitivity, during the 14-year window of observation, across the frequency bands surveyed, no civilization was broadcasting a narrowband signal powerful enough and appropriately directed enough for Earth's instruments to detect. Each of those qualifiers matters. The null result constrains a specific region of the search space. It does not rule out civilizations broadcasting on frequencies Arecibo could not monitor, or transmitting at power levels below its detection threshold, or aiming their beams in directions that did not include our solar system. But it narrows the possibilities, and the narrowing consistently points in the same direction. Detection is far harder than hope suggests. There is another dimension to the detection problem that rarely receives attention in popular discussions: frequency alignment. Electromagnetic radiation spans an enormous spectrum, from radio waves with wavelengths measured in meters to gamma rays with wavelengths smaller than atomic nuclei. A civilization choosing to broadcast a signal must select a specific frequency or range of frequencies. A civilization listening must also choose which frequencies to monitor. If the two choices do not overlap, neither civilization will ever detect the other, regardless of distance, power, or intent. SETI researchers have traditionally focused on frequencies near the hydrogen emission line at 1,420 MHz, reasoning that hydrogen is the most abundant element in the universe, and any scientifically minded civilization would recognize its spectral signature as a natural meeting point. This is a reasonable assumption. It is also entirely human. An alien civilization with different scientific traditions, different atmospheric conditions affecting which frequencies penetrate their skies, or different technological histories might choose a completely different frequency. They might communicate using lasers instead of radio. They might use neutrino beams, gravitational wave modulations, or methods we have not conceived. Every frequency choice we make is a bet. And every bet we place on one frequency is a bet we are not placing on millions of others. This challenge has motivated a parallel track of research known as optical SETI, the search for alien civilizations communicating through laser light rather than radio waves. The logic is appealing. Lasers are far more energy efficient than radio for point-to-point communication across interstellar distances. A sufficiently powerful laser pulse, even one lasting only nanoseconds, can outshine its host star for the brief duration of the flash, making it theoretically detectable across hundreds or thousands of light years by a telescope equipped with the right sensors. Several dedicated programs have searched for these optical technosignatures, including the Harvard All-Sky Optical SETI Survey and the Panoramic SETI Experiment at Lick Observatory, which uses an array of geodesic dome-mounted cameras to monitor wide swaths of the sky for brief, anomalous flashes of light. But optical SETI faces its own version of the alignment problem, and in some ways a more severe one. Laser beams are extraordinarily narrow. A laser designed for interstellar communication would produce a beam that, even after spreading over hundreds of light years, might illuminate a region only a few astronomical units across at the receiving end. This extreme directionality is precisely what makes lasers efficient. All the energy goes in one direction instead of spreading across the sky. But it also means the beam must be aimed with extraordinary precision at the target star system. A misalignment of a fraction of an arc-second could cause the beam to miss entirely. The transmitting civilization must not only know that the target system exists, but know its position with accuracy sufficient to hit it with a beam narrower than the width of a solar system viewed from 1,000 light-years away. And the receiving civilization must happen to be looking in the right direction at the right moment, with an instrument sensitive to the right wavelength during the nanoseconds when the flash arrives. Radio searches face alignment problems. Optical searches face alignment problems that are geometrically tighter. The technology that solves the energy problem simultaneously worsens the targeting problem. There is no free lunch in interstellar communication. Every gain on one axis of the detection challenge comes at a cost on another. More efficient transmission requires more precise aim. Broader coverage requires more energy. Longer transmission duration increases the chance of temporal overlap but demands sustained commitment of resources. The detection problem is not a single obstacle to be overcome. It is a system of interlocking constraints that resist optimization, because improving one parameter inevitably degrades another. The temporal alignment problem is equally severe and compounding. Even if two civilizations choose the same frequency, they must also be transmitting and listening during overlapping time windows. A civilization that broadcasts for 10,000 years and then falls silent will be detectable only during that 10,000-year window. A civilization that begins listening after the broadcaster has gone quiet will find nothing. The universe does not store signals. Radio waves do not pause and wait for someone to tune in. They pass through a region of space at the speed of light and continue onward forever. If no receiver is positioned in the right place at the right time, tuned to the right frequency, the signal is lost. It does not echo. It does not accumulate. It is simply gone. Now combine all of these barriers simultaneously. Two civilizations exist in the same galaxy. They are separated by 1,000 light years. Each one broadcasts on a specific frequency for a specific duration with a specific power level aimed in a specific direction. For detection to occur, the following conditions must all be satisfied at the same time. The broadcaster must be transmitting during a period that overlaps with the listener's operational lifespan. The signal must be powerful enough to remain above noise levels after crossing 1,000 light-years of interstellar space. The frequency must match what the listener is monitoring. The beam, if directed, must be aimed close enough to the listener's star to illuminate it. And the listener must have equipment sensitive enough to distinguish the signal from natural astrophysical sources and terrestrial interference. Failure on any single one of these conditions results in no detection. And these conditions are not independent. They compound multiplicatively. The probability of simultaneous success on all fronts is the product of each individual probability. If each condition has even a moderately low chance of being met, the combined probability collapses towards zero with alarming speed. This compounding explains something that puzzles many people about the search for extraterrestrial intelligence. We have been searching for decades. Our telescopes are increasingly powerful. Our algorithms are increasingly sophisticated. Why have we not found anything? The answer is not that aliens do not exist. The answer is that the detection problem is not a linear search that gets progressively easier with better tools. It is a multi-dimensional alignment problem in which every axis of alignment, spatial, temporal, spectral, directional, energetic, must be satisfied simultaneously. Improving one axis does not compensate for failure on the others. You can build the most sensitive radio telescope in the history of civilization, and it will find nothing if the nearest broadcaster went silent a century before you started listening, or if they transmit on a frequency you are not monitoring, or if their beam points 30 degrees away from your star. The profound consequence of all this is that even if civilizations are not especially rare, communication between them might be. The galaxy could contain 10,000 broadcasting civilizations right now, and each one could still sit in perfect silence from every other's perspective, not because their signals are too weak, not because their technology is too primitive, but because the alignment conditions required for mutual detection are so stringent that chance alone cannot reliably produce them across interstellar distances. Each civilization would occupy its own private bubble of silence, surrounded by a cosmos humming with signals it will never intercept. This realization transforms the Fermi paradox from a question about existence into a question about connectivity. The traditional formulation asks, where is everybody? The implicit assumption is that if civilizations exist, they should be detectable. But the physics of interstellar communication suggests a different framing. Everybody might be right where you would expect them, scattered across the galaxy in proportion to the number of habitable worlds and the probability of intelligence arising. The question is not where they are. The question is whether where they are and where we can detect them have any overlap at all. And the uncomfortable answer suggested by decades of null results and basic electromagnetic physics is that the overlap might be vanishingly small, even in a galaxy teeming with minds. There is one more dimension to this problem that does not involve physics at all. It involves information theory. Suppose, against all odds, a signal is detected. Suppose a radio telescope picks up an unmistakably artificial narrowband transmission from a star 1,000 light-years away. The signal is confirmed by multiple observatories. There is no doubt. Someone is out there. What happens next? The signal contains information, but information requires decoding, and decoding requires shared context. Human languages are mutually unintelligible without years of study, and they all evolved on the same planet from the same cognitive architecture. An alien signal would encode information structured by a mind that shares nothing with human cognition. No common evolutionary history, no shared sensory experience, no overlapping cultural references. The mathematics of prime numbers, often proposed as a universal language, could serve as a handshake, a proof of intelligence. But moving from "we know they are intelligent" to "we understand what they are telling us" is a gulf that no mathematical primer can reliably bridge. We have never successfully decoded a communication system designed by a mind fundamentally different from our own. We struggle with dolphin communication. We cannot decode the signals of species that share our planet, our evolutionary lineage, and our basic neurological structure. The expectation that we would immediately understand a message from a mind that evolved independently on a world we have never seen is not optimism. It is fantasy. And yet, even this decoding challenge assumes we receive enough signal to work with. A transmission from 1,000 light-years away, weakened by the inverse square law, filtered through interstellar dust, competing with natural radio sources and terrestrial interference, may arrive as a fragment, a few seconds of data, a partial pattern, enough to confirm artificial origin but not enough to extract meaningful content. We would know. Someone spoke. We would not know what they said. And we could not ask them to repeat it, because our request would take 1,000 years to arrive, and their reply, if they still existed to send one, would take another 1,000 years to return. The conversation would be over before it began. This is the architecture of cosmic silence. It is not built from a single overwhelming barrier, but from the accumulation of dozens of individually surmountable obstacles that become collectively insurmountable when multiplied together. Distance weakens signals. The inverse square law drains their energy. Frequency misalignment hides them. Temporal misalignment erases them. Directional misalignment diverts them. Decoding barriers obscure them. And the speed of light, the fastest possible carrier of information, ensures that even when everything else aligns, the delay between question and answer exceeds the lifespan of the cultures involved. But there is something even more fundamental lurking beneath all of these technical barriers. Something that does not depend on signal strength, telescope sensitivity, or transmission power. Even if the physics somehow cooperated, even if signals could cross the gap at sufficient strength, on the right frequency, aimed in the right direction, at the right time, there is a deeper problem that distance and delay alone cannot fully explain. Because the question is not just whether two civilizations can detect each other across space. The question is whether they can both be alive at the same time. And the answer to that question depends on something far more fragile than physics. It depends on how long civilizations last. And that fragility opens a chasm beneath the entire search for extraterrestrial intelligence that most people have never looked into. The Milky Way is approximately 13.6 billion years old. For most of that history, the galaxy was not a place where technological civilizations could exist. The first several billion years were dominated by population 3 stars, massive metal-poor furnaces that burned hot and died young. These primordial stars contained almost no elements heavier than helium, because those heavier elements had not yet been forged. Carbon, oxygen, nitrogen, silicon, iron, the ingredients required for rocky planets and complex chemistry, did not exist in significant quantities until generations of stars had lived, fused lighter elements into heavier ones within their cores, and scattered those products across space through supernova explosions. Planet formation requires these heavy elements. Life as we understand it requires them in abundance. The galaxy needed billions of years of stellar recycling before the raw materials for biology were widely available. Conservative estimates suggest that conditions suitable for habitable rocky planets did not become common until roughly 8 to 10 billion years ago. This means the window during which technological civilizations could theoretically arise spans approximately 8 to 10 billion years. That is the stage. Now consider the actors. Human civilization has possessed the technology to produce detectable electromagnetic emissions for approximately 100 years. Radio broadcasting began in the early 20th century. Radar systems followed. Television transmissions added to the output. For roughly a century, Earth has been announcing its technological presence to the cosmos through electromagnetic radiation leaking into space. 100 years out of a window of 10 billion years. To grasp the ratio, imagine the entire history of the habitable galaxy compressed into a single calendar year. January 1st represents the moment conditions first allowed technological life. December 31st represents today. In that calendar, Earth's entire technological lifetime occupies the final third of the final second of the year, not the final minute, not the final 10 seconds. Roughly 316 milliseconds, a fraction of a second so brief it is shorter than a single human heartbeat. Everything humanity has ever broadcast into space fits inside a sliver of time barely long enough to blink. This is the overlap problem. For two technological civilizations to detect each other, they must not only exist in the same galaxy at achievable distances, they must also exist at the same time. And not just exist simultaneously in a biological sense. They must overlap in their technologically detectable phase. Both civilizations must be actively producing or monitoring electromagnetic signals during the same window. If one civilization broadcast for 10,000 years and then collapsed, and a second civilization arose 5 million years later, they would never know about each other. The galaxy would have hosted both of them. They might have occupied neighboring star systems, and their mutual ignorance would be absolute. The mathematics of temporal overlap are merciless. Suppose civilizations arise randomly throughout the galaxy's habitable history, each one lasting an average of 10,000 years in its technologically active phase. 10,000 years is generous by the standards of human history, but brief by cosmic standards. Spread across 10 billion years of habitable time, each civilization occupies 1/1,000,000th of the total window. For two such civilizations to overlap, their individual millionth fractions must coincide. If civilizations arise infrequently, say one new civilization appearing every 1,000 years somewhere in the galaxy, then at any given moment only about 10 civilizations exist simultaneously. 10 civilizations scattered across a galaxy containing 400 billion stars spread across 100,000 light-years. The average separation between those 10 simultaneous civilizations would exceed 10,000 light-years. A round-trip signal at that distance takes more than 20,000 years, which is twice as long as each civilization lasts. They cannot even complete a single exchange of messages before one or both have vanished. Increase the birth rate. Suppose 100 civilizations exist simultaneously. The average separation drops to roughly 5,000 light-years. A round-trip message still takes 10,000 years, matching the entire assumed civilizational lifespan. Even with 100 neighbors sharing the galaxy at the same time, the communication delay exceeds the window during which either party remains capable of participating. The galaxy is not merely large. It is large in a way that is specifically calibrated to defeat the overlap between civilizational lifespans and signal travel times. This is not a coincidence or a conspiracy. It is a geometric consequence of distributing short-lived phenomena across an enormous volume where information travels at a finite speed. The 2026 study by Rava and Rouhani, published in monthly notices of the Royal Astronomical Society, formalized this reasoning with quantitative rigor. The researchers modeled the expected number of coexisting civilizations as a function of civilizational lifespan and the probability that a habitable planet produces technological intelligence. Their central finding was stark. Civilizational lifetimes in the range of 5,000 to 100,000 years are, in their words, fully consistent with the Fermi paradox. Multiple civilizations may exist sequentially or even overlap in time, yet still fail to detect one another due to insufficient longevity for communication or travel. The galaxy does not need to be empty to appear empty. It only needs to be populated by civilizations that do not last long enough to find each other. The silence we observe is not evidence of absence. It is evidence of brevity. This conclusion carries a haunting implication. The galaxy may have already hosted thousands of technological civilizations across its history. Some of them may have built vast infrastructures, explored their local stellar neighborhoods, composed symphonies, developed philosophies, asked the same questions about cosmic loneliness that we ask now. And every single one of them may have arisen, searched the sky, found nothing, and perished without ever learning that others had come before or would come after. Each civilization would experience itself as alone in the universe. Each would face the same silence. Each would wonder whether the emptiness was real or whether they simply lacked the tools, the patience, or the luck to find the others. And each would eventually go dark, its transmissions fading into the background noise, leaving no trace that any subsequent civilization could detect. The abstraction of civilizational lifespan becomes less abstract when you examine the historical record. Earth provides the only dataset we have, and it is not encouraging. Every complex civilization that has arisen on this planet has eventually collapsed, fragmented, or been absorbed by a successor culture. The pattern is so consistent that historians and archaeologists treat civilizational decline not as an anomaly, but as a structural feature of complex societies. The Akkadian Empire, often cited as the first true empire in human history, unified Mesopotamia under a centralized government around 2300 BCE. It was powerful, literate, and administratively sophisticated. It collapsed within approximately 2 centuries, likely driven by a combination of prolonged drought, internal rebellion, and invasion by surrounding peoples. 200 years from rise to ruin. The Neo-Assyrian Empire, one of the most militarily dominant states of the ancient world, controlled territory stretching from Egypt to Iran at its peak. It endured in its imperial form for roughly 3 centuries, before collapsing with startling rapidity between 612 and 609 BCE. Babylon and its allies dismantled the empire within a few years, erasing a political structure that had taken centuries to build. Classical Rome, from the traditional founding of the Republic in 509 BCE to the fall of the Western Empire in 476 CE, lasted approximately 1,000 years if you count both republican and imperial phases. This is exceptional longevity by historical standards. But Rome's technological civilization, the phase during which it possessed advanced engineering, extensive literacy, long-distance trade networks, and centralized infrastructure, occupied a shorter window. The advanced aqueduct systems, road networks, and architectural achievements of Imperial Rome degraded significantly in Western Europe within a few centuries of the empire's collapse. The technological capabilities were not independently preserved. They were lost and had to be rediscovered or reinvented centuries later. The classic Maya civilization, which developed sophisticated mathematics, astronomy, writing, and monumental architecture across the Yucatan Peninsula, experienced a dramatic collapse between roughly 800 and 1000 CE. Cities were abandoned, populations declined. The causes remain debated, with candidates including drought, warfare, deforestation, and political fragmentation. but the pattern is familiar. A complex society that sustained itself for several centuries reached a threshold it could not survive and disintegrated within a few generations. The Ottoman Empire endured for approximately 6 centuries, from the late 13th century to the early 20th century. This is an impressive span, but the empire's character transformed so completely across those centuries that early Ottoman society would be barely recognizable to its final citizens. And when the collapse came, it came within the span of a single human lifetime, driven by military defeat, internal revolution, and the redrawing of maps by external powers. What these examples share is not a single cause of decline, but a common vulnerability. Complex civilizations are maintained by intricate networks of resource distribution, social cooperation, and institutional continuity. These networks are robust within certain ranges of stress but fragile beyond them. Drought, disease, invasion, resource depletion, internal corruption, technological disruption, any of these can push a complex system past its resilience threshold. And once decline begins, the same interconnectedness that made the civilization powerful accelerates its collapse. Supply chains fail, specialized knowledge is lost, populations disperse. Within a few generations, the civilization that seemed permanent reveals itself to have been temporary all along. If this pattern applies to technological civilizations generally, and there is no evidence that it does not, then the Drake equation's L variable is not a free parameter that can be set to any convenient value. It is constrained by the structural fragility that appears to be inherent in complex, interconnected societies. A civilization that lasts 10,000 years would be an extraordinary outlier by the standards of Earth's historical record. One that lasts 100,000 years would be unprecedented by a factor of 100. The assumption that alien civilizations routinely endure for millions of years is not merely optimistic. It requires positing that alien societies have solved a problem that no human civilization has ever solved: the problem of permanent stability in a complex system. And the physical environment of any planet, with its volcanic eruptions, asteroid impacts, climate shifts, and stellar evolution, provides a steady supply of external shocks that test that stability on every timescale. But perhaps civilizations last longer than 10,000 years. Perhaps some of them endure for millions of years, building technologies so advanced that they can bridge any gap. This is a common rebuttal to the overlap argument, and it deserves serious consideration. If even a small fraction of civilizations achieve extreme longevity, they would dominate the galactic landscape. A civilization lasting 100 million years would overlap with thousands of shorter-lived neighbors. It would have time to send signals to every star in the galaxy and wait for replies from thousands of them. The Fermi paradox becomes more acute, not less, when you assume long-lived civilizations, because their absence becomes harder to explain. If they exist, where are they? The fact that we observe no evidence of such civilizations, despite decades of searching, suggests one of several possibilities. Perhaps long-lived civilizations are vanishingly rare. Perhaps they exist but choose not to broadcast or are undetectable by our current methods. Perhaps they are detectable but we have not yet looked in the right place at the right time. Or perhaps the very concept of a million-year civilization is physically impossible because the processes that create technological intelligence also create the conditions for its eventual collapse. Each of these possibilities is consistent with the observed silence. None of them offer comfort to a civilization hoping to find a neighbor within reach. The detectability problem deserves special attention because it operates independently of distance and lifespan. A civilization could exist next door in cosmic terms, occupy the nearest habitable star system, and still remain completely invisible if it does not produce the right kind of signatures at the right intensity. Detectability is not an inherent property of a civilization. It is a relationship between what the civilization emits and what the observer can perceive, and that relationship depends on technology, attention, and alignment in ways that stack relentlessly against discovery. Consider the TRAPPIST-1 system, one of the most intensely studied planetary systems in modern astronomy. Located approximately 40 light-years from Earth, TRAPPIST-1 is an ultra-cool red dwarf star orbited by 7 roughly Earth-sized planets, 3 of which sit within the star's habitable zone, where liquid water could theoretically exist. The system has been a primary target for the James Webb Space Telescope since its deployment, precisely because it represents the best nearby laboratory for studying potentially habitable worlds. If there were ever a case where proximity and attention should produce definitive answers about a planet's capacity to host life, this would be it. 40 light-years is practically next door. 7 planets to examine. The most powerful space telescope ever built, specifically designed for this kind of observation. And the results illustrate just how difficult atmospheric characterization remains even at close range. In 2025, a team led by Anna Glidden at the Massachusetts Institute of Technology used JWST to collect transmission spectra of TRAPPIST-1e, the planet most favorably positioned within the habitable zone. The data were contaminated by features from the host star's surface, a known challenge when observing planets around active red dwarfs. After accounting for this contamination, the team found that the data did not lean strongly in favor of or against the planet having an atmosphere. Hydrogen-rich atmospheres were excluded. Venus-like and Mars-like compositions were disfavored, but nitrogen-dominated atmospheres with traces of methane and carbon dioxide remained fully permitted. The result was not a detection. It was not a non-detection. It was irreducible ambiguity, the best telescope humanity has ever built, unable to definitively determine whether a planet 40 light-years away has an atmosphere at all. Then, in April 2026, a study published in Nature Astronomy by Gillon and collaborators delivered even more sobering news. JWST thermal phase curve observations of the 2 innermost TRAPPIST-1 planets, B and C, revealed that both emit thermal radiation consistent with bare rocky surfaces lacking thick atmospheres. Models with surface pressures above approximately 1 bar were strongly disfavored for both worlds. The 2 planets closest to the star appear to be stripped, airless rocks baking under radiation from their host. This does not rule out atmospheres on the more distant habitable zone planets, E, F, and G. But it demonstrates that even in a system practically designed for our telescopes, in our nearest well-studied planetary laboratory, the question of habitability remains agonizingly unresolved. Now extend this difficulty outward. If JWST struggles to characterize atmospheres at 40 light-years, what hope do we have of detecting biosignatures or technosignatures at 500, 1000, or 5000 light-years? The answer, with current and near-future technology, is effectively none. Atmospheric spectroscopy requires observing a planet as it transits in front of its star, measuring the tiny fraction of starlight filtered through the planet's atmosphere. The signal is minuscule, often measured in parts per million of the total stellar brightness. At greater distances, the host star is dimmer, the transit signal is smaller, and the noise level is higher. Beyond a few hundred light-years, individual planetary atmospheres become uncharacterizable by any instrument that currently exists or is being planned for the next several decades. The Habitable Worlds Observatory, a proposed NASA flagship mission designed specifically for direct imaging and atmospheric characterization of Earth-like exoplanets, is not projected to launch until the 2040s at the earliest. Even when it flies, its reach will be limited to stars within a few tens of light-years, a tiny sphere containing a few thousand stellar systems. Beyond that sphere, planets are points of reflected light too faint and too close to their stars to resolve. This means that our ability to determine whether a nearby world harbours life, let alone technological intelligence, is confined to our immediate stellar neighbourhood. And our immediate stellar neighbourhood, in galactic terms, is microscopically small. The volume within 100 light-years of Earth contains roughly 14,000 stars. That sounds like a large number until you compare it to the galaxy's total population of 400 billion. 14,000 amounts to roughly 1 in 30 million of the Milky Way's stellar content. If the nearest civilization is 1,000 light-years away, It lies far outside the volume we can currently characterize in any detail. We could not detect its atmosphere. We could not identify biosignatures in its air. We could not photograph its surface. The only way we could know it exists is if it is actively broadcasting powerful electromagnetic signals in our direction. And the probability of that alignment, as we have already seen, is low enough to explain decades of silence without requiring the absence of alien intelligence. There is a concept that captures the temporal dimension of this detection problem with particular clarity. It is called the contact era, developed in work by Claudio Grimaldi and explored further by subsequent researchers. The idea is straightforward. A civilization begins emitting detectable electromagnetic radiation at some point in its history. Those emissions expand outward at the speed of light, forming an expanding sphere called the radiosphere. Earth's radiosphere is currently about 100 light-years in radius, a bubble of electromagnetic noise centered on our solar system, expanding at the speed of light in every direction. Any civilization within that sphere whose instruments are sensitive enough could, in principle, detect our presence. But 100 light-years is tiny. The galaxy is 100,000 light-years across. Our radiosphere has reached less than 0.1% of the galaxy's diameter. The overwhelming majority of stellar systems, including any that might host civilizations, lie far beyond the edge of our electromagnetic announcement. The contact era represents the time after a civilization begins broadcasting, at which the probability of another civilization detecting its signals becomes significant. Grimaldi's analysis showed that unless civilizations are extraordinarily abundant, the contact era spans hundreds to thousands of years. For a galaxy containing 10,000 simultaneous civilizations, the contact era for any individual civilization is roughly 300 to 1,000 years. This means that for the first several centuries of its electromagnetic existence, a civilization is functionally invisible to the rest of the galaxy. Its signals have not traveled far enough to reach any likely listener. Earth is currently 100 years into its electromagnetic lifetime. If the contact era is 300 years, we have not yet existed long enough for our presence to become statistically likely to reach anyone. We are shouting into a room that has not yet heard us, not because the room is empty, but because our voice has not had time to reach the walls. This framework reveals a cruel irony. The civilizations most likely to detect each other are the ones that last the longest. But lasting long is precisely what civilizations may be worst at. Human history offers a disquieting dataset. Every complex civilization that has ever existed on Earth has eventually collapsed, transformed, or been absorbed by a successor. The average lifespan of a major empire or civilization is measured in centuries, not millennia. Technological civilization, defined by industrial capability and electromagnetic emission, has existed for roughly 200 years. Whether it will exist for another 200, another 2,000, or another 20,000 is an open question that depends on variables ranging from nuclear arsenals to climate stability to asteroid impacts, to the emergence of artificial superintelligence. The Drake equation's final variable, L, the average longevity of a communicative civilization, is the single most important number in the entire search for extraterrestrial intelligence. And it is the one we know least about. We have exactly one data point, ourselves, and we do not yet know our own value of L, because we are still in the middle of our story. The overlap problem extends beyond electromagnetic detection to physical visitation. Even if a civilization develops interstellar travel capability, its ability to contact neighbors depends on the same temporal alignment. A probe traveling at 1% of the speed of light, which is orders of magnitude faster than anything humans have built, takes 10,000 years to cross 100 light-years. If the target civilization arose 50,000 years before the probe launched and lasted 10,000 years, it will have been extinct for 40,000 years before the probe arrives. The probe reaches a dead world. Whatever it was supposed to find is gone. Only ruins would remain. If even those survive atmospheric erosion, geological recycling, and the quiet entropy that unmakes every structure over deep time. Some researchers have proposed that civilizations might leave durable artifacts, probes, beacons, or megastructures that persist long after their creators vanish. Freeman Dyson's hypothetical Dyson spheres, structures built to capture the entire energy output of a star, have been proposed as potential technosignatures that would outlast any civilization. But searches for anomalous infrared signatures consistent with Dyson spheres, including surveys covering hundreds of thousands of stars, have produced no confirmed candidates. Either such structures are not being built, or they are built in ways our instruments do not recognize, or they are so rare that our surveys have not yet covered the right stars. In any case, durable artifacts do not solve the overlap problem. They merely change it from, can we detect a living civilization, to, can we detect the remains of a dead one? And detecting remains, even if achievable, does not produce contact. It produces a monument, a gravestone, evidence that someone was here once and is here no longer. There is a final dimension of the overlap problem that operates at a subtler level than raw timing. Even when two civilizations coexist in time and space, they must also overlap in technological orientation. Not all civilizations may pass through a phase in which they emit detectable electromagnetic radiation. Human civilization has been electromagnetically loud for about a century, but this loudness may be temporary. As communication technology advances, societies tend to shift from broadcast to point-to-point transmission. Fiber optics replace radio towers. Directed signals replace omnidirectional broadcasts. A sufficiently advanced civilization might communicate entirely through methods that produce no detectable leakage, tight beam lasers, quantum encrypted channels, or technologies we cannot anticipate. Such a civilization would be technologically active but electromagnetically silent. From our perspective, it would be invisible. The window during which a civilization is both technologically capable and electromagnetically detectable may be far shorter than its total lifespan, perhaps only a few centuries out of a 10,000-year civilizational arc. This shrinks the effective overlap window even further, reducing the probability that two civilizations happen to be in their detectable phases simultaneously. This going dark phenomenon deserves closer examination because it introduces a barrier that operates independently of civilizational lifespan. A civilization that endures for 100,000 years but is electromagnetically loud for only 200 of those years presents essentially the same detection profile as a civilization that exists for only 200 years. Total. From the perspective of an outside observer scanning the sky, both civilizations are visible for the same brief window. The rest of the time, they are ghosts, present but undetectable. The trajectory of human communication technology suggests this transition is not speculative. In the 1950s and 60s, Earth's electromagnetic leakage was dominated by powerful analog television transmitters broadcasting megawatts of power from tall towers in all directions. These signals were genuinely omnidirectional and, while weak by interstellar standards, represented the loudest unintentional electromagnetic emissions in Earth's history. By the 1990s, cable television had begun replacing broadcast transmission. By the 2000s, streaming services delivered over fiber optic cables had started displacing both. Cellular networks, while ubiquitous, use low-power transmitters designed to reach nearby towers, not distant receivers. Each generation of communication technology is more efficient, more targeted, and quieter. The trend is unmistakable. Humanity is becoming electromagnetically dimmer with each passing decade, not because we communicate less, but because we communicate more efficiently. Efficiency means directing energy where it is needed, rather than spraying it in every direction. And directing energy means producing less detectable leakage. If this trajectory continues, Earth's accidental electromagnetic signature may peak within a century or two of the onset of radio technology and then decline toward undetectability. A civilization observing our solar system from 100 light-years away in the year 2100 might have noticed a faint but measurable increase in radio noise from our direction, beginning in the 1920s. By 2100, that noise may already be fading. By 2200, it may be gone entirely, replaced by a communication infrastructure so efficient that nothing escapes into space. From the outside, Earth would appear to have gone silent, not because civilization ended, but because it matured. Project this onto a galactic population of civilizations. If the electromagnetically loud phase lasts only 1 to 3 centuries out of a civilizational lifespan of 10,000 years, then at any given moment, only 1 to 3% of all existing civilizations are detectable through their leakage. The overlap window shrinks accordingly. 2 civilizations that each broadcast for 200 years out of a 10,000-year lifespan must not only overlap in their total existence, but overlap specifically in their brief, loud phases. The probability of this double overlap is the product of 2 already small probabilities, yielding a combined chance so low that even a galaxy hosting thousands of simultaneous civilizations might contain 0 pairs that are mutually detectable at any given moment. The galaxy could be crowded with mature, quiet civilizations that passed through their detectable phase long ago and now sit in electromagnetic silence, surrounded by neighbors in exactly the same condition. Everyone listening, no one broadcasting, the cosmos reduced to a waiting room where every civilization sits in silence, assuming the room is empty. There is one additional dimension of the overlap problem that operates at an even more fundamental level than technology or electromagnetic leakage. Even civilizations that coexist in both time and space might fail to recognize each other's signals because they operate on incompatible timescales. Human communication unfolds in seconds. Our radio transmissions pulse at frequencies measured in millions or billions of cycles per second. Our data is encoded in rapid modulations that carry meaning through their precise timing. When SETI researchers search for alien signals, they look for patterns that match this temporal grain. Narrowband signals that persist for seconds or minutes, pulses that repeat at intervals detectable within an observation session, lasting hours. But there is no reason to assume that an alien civilization would communicate on human timescales. Biology determines the pace of cognition. On Earth, neural signals propagate at speeds ranging from roughly 1 to 100 meters per second, depending on the type of nerve fiber. This sets the tempo of human thought and, by extension, the temporal structure of human communication. A civilization evolved from organisms with fundamentally different neural architectures might think and communicate on radically different timescales. A biochemistry based on slower metabolic processes could produce minds that operate on timescales of hours or days rather than milliseconds. Their transmissions might modulate so slowly that each symbol takes weeks to complete. Observed by human instruments over a standard observation window of minutes or hours, such a signal would appear as a featureless constant tone, indistinguishable from natural astrophysical emissions. It would be data, rich with meaning, passing through our receivers without triggering a single detection algorithm, because our algorithms are built to recognize patterns that fluctuate on human timescales. The reverse is equally true. A civilization with faster cognition than ours, perhaps one based on electronic or photonic substrates rather than biological neurons, might communicate in bursts so rapid that each complete message occupies nanoseconds. To their receivers, human radio transmissions would appear as glacially slow variations in background noise, too sluggish to register as intentional communication. 2 civilizations sharing the same galaxy at the same time, transmitting on the same frequency, even aimed at each other, could still fail to achieve mutual recognition because the temporal resolution of their communication is mismatched by orders of magnitude. This is not the same as the frequency alignment problem, which concerns where in the electromagnetic spectrum civilizations transmit. It is not the same as the going dark problem, which concerns whether civilizations emit detectable radiation at all. It is a distinct barrier, the possibility that the temporal structure of alien communication is so different from ours that even a strong, well-aimed signal would pass through our detection systems as noise. The universe may not only separate civilizations by distance and time, it may separate them by the pace at which they think, ensuring that even overlapping, broadcasting neighbors remain mutually unintelligible. The cumulative weight of these overlapping failures creates a picture that is difficult to escape. The galaxy is vast, civilizations are brief. Signals travel at a finite speed through a medium that dilutes them into oblivion. Detection requires alignment across spatial, temporal, spectral, and directional axes simultaneously. The window during which any given civilization is both alive and detectable may span a few centuries out of a galactic history measured in billions of years. And even our best instruments can barely characterize the atmospheres of planets 40 light-years away, leaving the overwhelming majority of the galaxy's habitable worlds permanently beyond scrutiny. The overlap problem does not merely reduce the probability of contact, it reframes what contact means. In a universe governed by these constraints, contact is not a milestone that civilizations inevitably reach if they search long enough or build sensitive enough instruments. Contact is an accident, a statistical anomaly, a coincidence of timing, location, technology, and duration so precise that it may never occur even in a galaxy populated by thousands of civilizations across billions of years. The silence we hear when we point our telescopes at the sky is not necessarily the silence of an empty galaxy. It may be the silence of a galaxy full of voices that spoke at different times, in different directions, at different frequencies, and for too brief a span to ever hear each other. But there is one more layer to this story, one final realization that takes everything we have discussed, the distance, the delay, the overlap, the detectability failures, and fuses them into a single, irreducible conclusion about what it means to search for the nearest alien civilization in a cosmos built on these scales. That realization does not depend on whether aliens exist. It does not depend on how long they last. It depends on what the word near actually means when stripped of every comforting human assumption and measured against the architecture of the universe itself. Build the most generous scenario imaginable. Grant every optimistic assumption. Suppose a technological civilization exists right now, at this very moment, orbiting a star 1,000 light-years from Earth. Suppose it has endured for 50,000 years, making it extraordinarily long-lived by any reasonable estimate. Suppose it actively broadcasts powerful radio signals across a wide range of frequencies. Suppose its transmitters are aimed in our general direction. Suppose its electromagnetic output dwarfs anything humanity has ever produced. A beacon so powerful that it could be detected by instruments far less sensitive than our best telescopes. Suppose further that this civilization is curious, that it wants to be found, that it has invested substantial resources in announcing its presence to the cosmos. This is the dream scenario. Every variable turned to its most favourable setting. Every barrier lowered as far as plausibility permits. And even here, in this most forgiving of all possible configurations, meaningful contact remains impossible. The signal from this civilization, travelling at the maximum speed the universe allows, takes 1,000 years to reach Earth. The light we see from their star tonight departed while Europe was in the Middle Ages. If they aimed a transmission at us 1,000 years ago, that message is arriving now, carrying information about a civilization as it existed 10 centuries in our past. We cannot know what they look like today. We cannot know whether the government that authorized the transmission still exists. We cannot know whether the language it was written in is still spoken. We cannot know whether the civilization itself has survived the intervening millennium. We receive a postcard from a past that may already be a ruin, with no way to verify whether the sender is still alive. If we reply immediately, our response begins its own 1,000-year journey. It arrives in the year 3026. The total elapsed time between their original transmission and the arrival of our reply is 2,000 years. If they are patient enough to wait, and if their civilization endures another millennium beyond the moment they sent the original message, they receive our answer. The round-trip exchange of a single sentence, has consumed 20 centuries, 2 complete cycles of what humanity considers deep historical time. The rise and fall of Rome fits inside this pause. The invention of the printing press, the scientific revolution, the industrial age, the digital era, the entirety of modern civilization as we know it, all of it unfolds within the gap between question and answer. This is not a conversation. A conversation requires that each statement responds to the last, that meaning accumulates through exchange, that both parties occupy a shared frame of reference close enough in time for context to hold. What this scenario describes is something else entirely. It is 2 monologues separated by an abyss. Each civilization speaks into the void and waits for a reply that, when it arrives, addresses a version of themselves that no longer exists. The questions they asked may no longer be relevant. The answers they receive may no longer be comprehensible. The cultural, linguistic, and cognitive frameworks that gave the original message its meaning may have dissolved and been replaced by something unrecognizable. Both civilizations are speaking. Neither one is being heard. Not because the signal failed, but because the gap between utterances is wider than the lifespan of the context that gave those utterances meaning. And this, remember, is the best case, the most optimistic version of the scenario, the version where everything works, where the civilization is long-lived, powerful, intentional, and aimed at us. Strip away any single one of those generous assumptions, and the picture darkens rapidly. Reduce their lifespan to 10,000 years, a value consistent with the upper bounds suggested by recent research, and they may go silent before our reply arrives. Reduce their transmitter power to something comparable to our own, and their signal drowns in interstellar noise before reaching us. Remove the assumption of intentional broadcasting, and they become electromagnetically quiet, visible only during a brief window of leaky emissions that fades into undetectability within a few light years. Remove the directional alignment, and their signal passes through a region of space we are not monitoring, in a frequency band we are not scanning, during a decade when our instruments are pointed elsewhere. Each removed assumption does not merely reduce the probability of contact, it functionally eliminates it. The dream scenario is not a floor beneath which reality cannot sink. It is a ceiling that reality almost certainly never reaches. This is the point where the meaning of too far away must be understood in its fullest sense. When the title of this story says the closest alien civilization could be too far away, it does not merely mean too far to visit. It means too far for signals to cross within civilizational lifetimes. Too far for mutual detection to occur given realistic transmitter powers and receiver sensitivities. Too far for temporal overlap to be anything other than a statistical miracle. Too far for shared context to survive the transit. Too far for the word contact to retain any of the meaning we instinctively assign to it. Too far away is not a statement about kilometers or light years alone. It is a statement about the total architecture of separation that the cosmos imposes on any 2 civilizations attempting to bridge the gap between their existences. Distance is one dimension of that architecture. Time is another. Detectability is a third. The duration of technological activity is a fourth. The alignment of transmission and reception is a fifth. Each dimension independently threatens to make contact impossible. Together they form a barrier so comprehensive that the question shifts from "can we overcome it?" to "is there anything left to overcome?" The human mind resists this conclusion for reasons that run deeper than logic. We are a social species. Our survival across hundreds of thousands of years depended on our ability to form connections, build alliances, and communicate across distances. Loneliness is not merely uncomfortable for human beings. It is physiologically dangerous. Prolonged isolation damages cognition, weakens immune function, and shortens lifespan. Evolution built us to seek contact because contact meant survival. When we look at the night sky and imagine other minds looking back, we are not engaged in a purely scientific exercise. We are enacting a biological imperative. The desire to find someone out there is not a rational response to evidence. It is an emotional need encoded in our deepest neurological architecture, and this need colours every assessment we make about the probability of contact. We overestimate our chances because we cannot bear the alternative. This emotional bias explains why the public discourse around alien life consistently skews toward optimism in ways that the evidence does not support. Every newly discovered exoplanet in a habitable zone is greeted with headlines suggesting it could host life. Every ambiguous spectral signature is treated as a potential biosignature. Every null result from SETI is framed as, "We have not found anything yet," with the emphasis on yet, as though detection is inevitable and only the timing remains uncertain. The word yet carries enormous psychological weight. It implies a trajectory. It suggests that the current silence is temporary, that discovery is approaching, that the question is when, not whether. But yet is not a conclusion drawn from evidence. It is an expression of hope, sustained by the same cognitive wiring that once drove our ancestors to search for companions beyond the next ridge. The evidence, assessed without the filter of evolutionary longing, supports a more unsettling interpretation. The galaxy could be populated with civilizations. It could contain thousands of them, scattered across its spiral arms, each one a brief flicker of technological activity, lasting a few millennia against the backdrop of billions of years of cosmic time, and those civilizations could still be permanently isolated from one another. Not because the distances between them are insurmountable in some absolute physical sense, but because the combination of distance, delay, brevity, and detectability conspires to ensure that no two of them ever achieve meaningful awareness of each other's existence. The galaxy could be alive and still feel perfectly, irrevocably empty. This is the distinction that separates the thesis of this story from simpler claims about cosmic loneliness. The argument is not that aliens do not exist. It is not that space is big and travel is hard. Those statements are true but insufficient. The deeper argument is that the existence of alien civilizations does not imply the possibility of contact, and that nearest does not imply reachable. These are separate questions that popular discourse routinely conflates. The question, "Are we alone?" and the question, "Can we ever matter to another civilization, or they to us?" are not the same question. The first asks about the probability of life arising elsewhere. The second asks about the probability of that life ever intersecting with ours in a way that produces mutual awareness, shared knowledge, or any form of exchange. The answer to the first question might be an enthusiastic yes. The answer to the second might still be a devastating no. Consider what it would mean for the galaxy to contain 10,000 civilizations right now, scattered randomly through its volume. 10,000 sounds abundant. It sounds like a crowded galaxy, a cosmos buzzing with minds. But distribute 10,000 points randomly through a disk 100,000 light-years across and 2,000 light-years thick, and the average distance between nearest neighbours approaches 1,000 light-years. Each civilization sits inside a sphere of silence roughly 2,000 light-years in diameter, within which no other technological species currently exists. At the centre of that sphere, a civilization broadcasts, listens, searches and wonders. It does everything right. It builds the most powerful transmitters it can engineer. It constructs telescopes of extraordinary sensitivity. It scans the sky with patience and rigour, and it finds nothing, not because the galaxy is empty, but because its nearest neighbour is 1,000 light-years away, and a round-trip signal takes 2,000 years, and neither civilization lasts long enough to complete the exchange. Each one is surrounded by others. Each one is functionally alone. Proximity exists on the map. It does not exist in experience. The cruelest dimension of this scenario is its symmetry. If we are searching and finding nothing, they are searching and finding nothing too. Whatever loneliness we feel, they feel in equal measure. Whatever hope we invest in the possibility of contact, they invest the same hope with the same futility. Each civilization in this model is a mirror of every other, identical in its isolation, identical in its longing, identical in its inability to reach across the gap. They look at the same galaxy we do. They see the same stars. They ask the same questions, and they arrive at the same silence. The universe does not merely separate these civilizations. It ensures that each one experiences the separation as total, complete, and apparently permanent. No outside perspective exists from which the populated galaxy can be seen as populated. Every internal perspective sees only emptiness. There is a concept in philosophy called the veil of ignorance, typically applied to theories of justice. Behind the veil, you do not know your position in society, so you design systems that are fair to all positions. The cosmos imposes its own veil of ignorance on civilizations. Behind the cosmic veil, no civilization knows its position in the distribution. No civilization knows whether it has neighbors or how far away they are. No civilization knows whether the silence it experiences is the silence of an empty galaxy or the silence of a full galaxy in which everyone is too far apart to hear each other. The veil cannot be lifted from the inside. The only way to determine which kind of galaxy you inhabit is to detect a neighbor, and if the distances and timescales prevent detection, the veil remains in place forever. You live and die without ever knowing whether the cosmos was empty or teeming, whether your loneliness was a reflection of reality or merely a limitation of reach. This is where the word closest completes its collapse. On Earth, closest implies a relationship. The closest friend is someone you can call. The closest store is somewhere you can walk to. The closest hospital is a place that can save your life. Closest is the geography of relevance, a way of sorting the world into what matters now and what matters less. But in the cosmos, closest has been emptied of this relational meaning. The closest civilization is not one you can call, visit, or be saved by. It is not a neighbor in any functional sense. It is a statistical abstraction, the smallest entry in a table of distances that are all, without exception, too large for the word neighbor to apply. Calling it the closest civilization is like calling a star on the opposite side of the galaxy the nearest unreachable object. The superlative does not domesticate the distance. It merely ranks the impossible. And yet something in us refuses to let go of the word. Something continues to hear closest and feel a spark of possibility. This refusal is not irrational. It is human. We are the species that crossed oceans in wooden boats, that reached the South Pole on foot, that landed on the moon with computers less powerful than a modern wristwatch. Every barrier we have ever faced has eventually been overcome by some combination of ingenuity, persistence, and time. The instinct to believe that interstellar distances will eventually yield to the same forces is deeply embedded in our cultural identity. We are the species that solves problems. We are the species that reaches, but the universe is not a problem that scales with human effort. The speed of light is not a challenge to be overcome by better engineering. It is a boundary condition of reality, as fundamental as the existence of matter or the direction of time. No amount of ingenuity changes the fact that a signal sent today will not arrive at a star 1,000 light years away for 1,000 years. No technology accelerates photons. No engineering shortens the path. The delay is not a wall to be broken through. It is the structure of the medium through which all information must travel. Wishing it were otherwise does not make it otherwise. And building our hopes on the assumption that some future breakthrough will circumvent the speed of light is not optimism. It is the denial of physics in favor of psychology. It is choosing the story we prefer over the reality we inhabit. The same applies to civilizational lifespan. We do not know how long human civilization will endure. We might last another century or another million years. But the overlap problem does not depend on our specific lifespan. It depends on the relationship between lifespan and distance. Even if humanity endures for 100,000 years, an extraordinarily optimistic assumption, and the nearest civilization is 5,000 light years away, a round-trip message consumes 10% of our entire existence. We would complete at most 10 exchanges across our entire history, each one a decade-spanning ordeal of transmission, waiting, reception, and response, with the content of each message shaped by a civilization that has evolved significantly since the previous exchange. This is not communication, it is geology. The pace of information exchange matches the pace at which mountains erode and continents drift, meaning cannot survive transit through timescales this vast. By the time the 10th reply arrives, the first question belongs to a civilization so remote in the past that it might as well belong to a different species. So what is left? What does it mean to search for something that may exist but cannot be reached? What does it mean to call something closest when even the closest instance lies beyond every meaningful threshold of contact? Perhaps it means that the search itself is the point, not the discovery, not the handshake across the void, but the act of looking, the refusal to accept silence as an answer without first exhausting every avenue of investigation. Perhaps the value of SETI is not that it will find aliens, but that it forces us to confront the scale of our isolation with scientific honesty rather than mythological comfort. Perhaps the greatest discovery we make will not be the detection of an alien signal, but the confirmed understanding of why we never will. That understanding itself would be profound. It would tell us something about the structure of the universe that no other observation can provide, that the cosmos builds minds in isolation and keeps them there, not through malice but through geometry. There is a quiet terror in this conclusion that feels different from the ordinary vastness of space vertigo. The usual cosmic horror is the horror of emptiness. The universe is big, and we are small, and maybe no one else is out there. That is a familiar ache, one that generations of stargazers have felt. But the horror of this story is different. It is the horror of fullness without connection. The possibility that the galaxy is rich with life, abundant with civilizations, dense with minds thinking thoughts and asking questions and building beautiful, temporary structures of meaning, and that none of them will ever know about any of the others, not because they are too few, but because the distances between them are too large, the delays too long, the lifespans too short, and the windows of mutual detectability too narrow. The galaxy could be a library full of books written in languages no other reader will ever learn, shelved in rooms no other visitor will ever enter. This is the image that the title of this story ultimately points toward. The closest alien civilization could be too far away. Not merely in the trivial sense that interstellar travel is difficult, in the deeper sense that the cosmos does not merely separate civilizations by distance. It separates them by time, by detectability, by the fragility of their existence, and by the fundamental limits of information transfer in a universe where nothing moves faster than light. Even the nearest possible neighbour could be near only on a map, not in any dimension that permits contact, exchange, rescue, or companionship. Near is a concept that belongs to a species that evolved on a planet 8,000 miles across. The cosmos does not recognise it. There is one more possibility that must be examined before this story reaches its conclusion. What if we never detect a living civilization, but we detect the remains of a dead one? What if the nearest civilization was close, genuinely close, a few hundred light years away, but it existed 10,000 years ago, or 100,000, or 1,000,000? Could we find its ruins? Could the cosmos preserve enough evidence of a technological society for a later civilization to stumble upon it across the gap of time? The idea of cosmic archaeology, searching not for living minds but for the traces they left behind, has gained serious attention in recent years. The reasoning is straightforward. If civilizations are short-lived but relatively common across galactic history, the galaxy may contain far more dead civilizations than living ones. The ruins might outnumber the inhabitants by orders of magnitude, and some of those ruins could produce detectable signatures long after the civilization that created them has vanished. What might those signatures look like? Several candidates have been proposed. Industrial pollution offers one possibility. A civilization that burns fossil fuels or engages in large-scale chemical processing would alter its planet's atmospheric composition. Chlorofluorocarbons and certain other industrial compounds have no known natural sources and would constitute unambiguous evidence of technological activity if detected in an exoplanet atmosphere. Other chemicals like nitrogen dioxide occur naturally, but at levels far below what industrial civilization produces. If a sufficiently powerful telescope could measure the atmospheric spectrum of a planet hundreds of light years away and detect chemicals at concentrations that have no plausible natural explanation, it would constitute evidence of past or present industrial activity. The challenge is sensitivity. These chemicals would likely be present in trace concentrations, parts per billion or less, and detecting them requires resolving spectral features that are orders of magnitude fainter than the signatures we struggle to measure at 40 light-years with JWST today. The Habitable Worlds Observatory, if it launches in the 2040s, might be capable of this kind of atmospheric forensics for planets within a few tens of light-years. Beyond that range, even industrial pollution fades below the threshold of any planned instrument. Abandoned megastructures offer another category of potential ruin. A Dyson sphere, or swarm, a hypothetical structure built to capture a significant fraction of a star's energy output, would alter the star's observable properties. It would reduce visible light output while increasing infrared emission, as captured energy is re-radiated as waste heat. Surveys searching for this infrared excess have examined hundreds of thousands of stars. Multiple surveys have searched for anomalous infrared excess consistent with Dyson structures, including a 2015 study by Griffith and collaborators that examined roughly 100,000 galaxies using data from the Wide Field Infrared Survey Explorer, and subsequent studies by Suazo and collaborators in 2022 and 2024 that search millions of individual stellar sources using combined data from WISE and the Gaia spacecraft. No confirmed Dyson sphere signatures have been identified in any of these surveys. Partial Dyson structures, swarms covering only a fraction of the star, might produce subtler signatures that current surveys cannot yet distinguish from natural phenomena like circumstellar dust. The absence of confirmed detections does not prove that megastructures do not exist, but it constrains their abundance. If even 1% of past civilizations built structures of this scale, we would expect to find at least some candidates among the hundreds of thousands of stars surveyed. Their absence suggests either that such structures are extraordinarily rare, that they are built in ways our instruments do not recognize, or that civilizations capable of building them are far less common than optimistic estimates suggest. There is a more poignant possibility still. What if the ruins are there, but they are simply too fragile to persist? On Earth, the decay timescales of technological artifacts are measured in centuries to millennia, not millions of years. Steel corrodes, concrete crumbles, electronic components degrade, plastics photodegrade under ultraviolet radiation. In the absence of active maintenance, the physical infrastructure of a technological civilization erodes and is eventually recycled by geological and atmospheric processes. A planet that hosted a technological civilization 1,000,000 years ago might show no surface trace of that civilization today. Erosion, tectonic activity, volcanic resurfacing, and biological overgrowth would erase every structure, every road, every artifact. The only surviving evidence might be subtle chemical anomalies in sedimentary rock layers or isotopic signatures in ice cores, evidence so faint that it could only be detected by landing on the planet and drilling into its geological record. From interstellar distances, such evidence would be completely invisible. This means that the window for detecting a dead civilization's ruins may be almost as narrow as the window for detecting the civilization itself. A planet whose industrial civilization collapsed 10,000 years ago might retain detectable atmospheric anomalies for a few centuries before natural chemistry scrubs them away. A partial Dyson structure might persist for longer, perhaps millions of years, before orbital decay and micrometeorite bombardment disperse its components. But even these longer-lasting signatures eventually fade. The cosmos does not preserve monuments, it dissolves them. Given enough time, every trace of every civilization is erased, return to the background noise of natural astrophysical processes. The galaxy's ruins, like its living inhabitants, are temporary. And this leads to the most haunting version of the contact failure. The nearest civilization might have existed close to us in space, a few hundred light years away, orbiting a star we can see tonight. It might have built cities, developed science, asked the same questions we ask. And it might have died 10,000 years ago, its atmosphere already scrubbed clean of industrial signatures, its structures already eroded beyond recognition, its electromagnetic emissions long since dispersed into the interstellar background. We look at its star and see nothing unusual. We analyze the light from its planets and find no anomalies. Every instrument we possess reports the same conclusion: an ordinary stellar system, unremarkable, uninhabited. And the conclusion is wrong. Someone was there. They were close. They were real. And we will never know, because the evidence of their existence has been reclaimed by the same physical processes that will eventually reclaim the evidence of ours. This is perhaps the deepest meaning of too far away. Not just too far in space, not just too far in time, but too far in the persistence of evidence itself. The cosmos separates civilizations not only by distance and duration, but by the decay of every trace that either one existed. Even the nearest civilization, even the closest one in both space and time, might leave no mark that any subsequent civilization could find. The library does not merely contain books in unreadable languages shelved in unreachable rooms. Some of the books have already crumbled to dust, and the rooms have been swept clean. The search will continue. Telescopes will scan new frequencies, surveys will cover more stars, instruments will grow more sensitive. And perhaps one day, against every probabilistic expectation, a signal will emerge from the noise, unmistakably artificial, undeniably alien. If that moment comes, it will be the most important event in human history. It will confirm that we are not the only minds the universe has produced. It will shatter our cosmic solitude. And then the delay will begin. The long, terrible wait for a reply that may take centuries or millennia to arrive, from a sender that may no longer exist, carrying meaning that may no longer translate. The nearest alien civilization might be out there right now, orbiting a quiet star in a spiral arm we can see on a clear night, wondering about the silence of their own skies, building instruments to search for us while we build instruments to search for them. Two civilizations reaching toward each other across a gap that light itself needs 1,000 years to cross. Both of them calling the other the closest. Both of them wrong about what that word means. Both of them too far away to ever know the difference.